We've spent a number of days now looking at one-dimensional multi-force problems. Things like elevator problems, things like pulley problems, things like inclined plane problems, and I think we've done a pretty good job. Okay, I think by the end of the week last week, I think we're in pretty good shape for that stuff. We'll find out tomorrow when we have ourselves a little quiz on that. Now what we're going to look at is two-dimensional force problems. We call them non-collinear force problems, okay, versus the one-dimensional collinear force problems. For instance, maybe we get a problem like this. Maybe it's Halloween coming up on Thursday. Wouldn't be Halloween if it didn't all of a sudden turn cold, right? -9 or whatever it is right now. Okay, maybe we got a problem where here's a bag of candy, and we pull it in this direction, and somebody pulls it in this direction, and then somebody pulls it out in this direction, and we want to find out what happens to that bag of candy. That's a two-dimensional problem because we've got forces going everywhere, not just forces going this way, and this way, and this way in one dimension. Okay, how would we deal with that? Or maybe you've got a problem. Yesterday I took my my 2-year-old son over to Morris Gibson School to go sledding. I took him over on this on one of those GT snow racers. I didn't let him go down the hill on one of those GT snow racers. There's only 2, but I took him over on one of them. So here's the sled. Okay. Here's the seat, whatever, and then there's a rope on the front that I was pulling with. The rope goes like this. So there's force of friction like this. There's gravity and a normal force like this, but yet I'm pulling him with the rope at an angle of, I don't know what the angle was, let's say 30 degrees. How do we deal with that? That's a two-dimensional problem as well, because I'm pulling him at an angle of 30 degrees as opposed to just straight to the right, like most of the problems we've done so far have been. Right? If we did a problem, treated this like we did last week, then I would have been pulling him like this. And it's pretty difficult to pull a sled like that. You have to be crawling on the ground in order to do that. What if we have a problem where here's a building, the side of a building, and then there's kind of this outcropping, the roof of a building, and we got a sign hanging down off of the roof like this. Maybe there's, let's see, maybe there's the sign hanging like this. Okay, here's my sign. Okay, there's a rope pulling in this way or a cable pulling in this way, and then there's a cable pulling in this way, and then there's gravity acting this way. Okay, how do we deal with that? How do we deal with these problems where there's more than one force acting, but they're acting in two dimensions? Well, the first thing we do is the same as we've always done. When we have more than one force acting, what do we always do first? Forget about one dimension, two dimension. What do we do if there's 2 or 3 or 4 forces acting on an object? Even before we find the net force. Okay, you're on the right track because we are going to get there. But even before we do that, what are we going to do? Travis? Let's draw a free body diagram. So we've got that problem where maybe I'm pulling on the sled like this. Okay, there's a force of friction like this. There's gravity and there's a normal force, right? Draw the free body diagram. Maybe we've got that problem where we're pulling on the bag of candy in different directions. There's a force like this, there's a force like this, there's a force like this. Whatever the forces are, let's draw all the forces. Now, Rutger said a minute ago, he was wrong about what we do first, but he wasn't wrong about what we do next. He said we should do the sum of the forces thing. We do. We have to do that. We have to add up all these forces to get the net force. Add this force to this force to this force. Add this force to this force to this force to this force. The problem is, adding them together in one dimension is pretty straightforward, pretty easy. F net is equal to the sum of the forces. Adding them together in 2 dimensions is a little bit harder because we have to add them vectorially. Here's what I want you to do. Whenever you see a problem involving more than one force in more than one dimension, I want you to break it up into x's and y's. Make sense? Then I want you to do F net is equal to the sum of the forces for both of them. FA plus FB plus whatever we got. Get the net force for X, get the net force for Y, and then what do you think you're going to do with them once you've got the X and the Y net force? You guys know this. Even though you haven't done a problem like this before, you know exactly what's going to come next. Once you get the X component net force and the Y component net force, what are you going to do with them? You're going to combine them in a vector diagram and find the hypotenuse, and then use the inverse tan function to find the angle. Just like we did back with displacement vectors and velocity vectors in Unit 1. Does that make sense? So we're doing the same thing as we did last week. F net is equal to the sum of the forces. We're just doing it twice. We're doing it for the X and for the Y instead of either X or Y. Remember last week, it was either on this plane or it was on this plane. We did either X or Y. Now we've got problems involving both planes, so we're doing not X or Y, we're doing X and Y. Okay? The best way to do this, is to do an example. We'll do a few examples, actually, but we'll do one to start us off. 3.3, page 133. We've got a canoe here that we're pulling in two different directions. We're pulling it 20 degrees upwards, 20 degrees downwards. Doesn't look like there's any friction here. Let's find the net force. Let's find the net force on this canoe. Draw my free body diagram. There's only two forces acting here. Let's call this F1. Let's call this F2. Look back to that example 3.2 on 132, and we see that F1 was 60 newtons. F2 is 60 newtons. And there was, in fact, a force of friction that was 85 newtons. It's going to act backwards, right? We'll call that FF, and its value is 85 newtons. What's the net force? What's the net force? Well, again, we have to break this up into X and Y components, and then do F net is equal to the sum of the forces. Let's first get rid of these funny angles here, because we don't like funny angles. Remember what we said back when we did displacement vectors? We don't like funny angles. Let's get rid of them. We're going to do that by drawing a little aside over here. We've got 60 newtons at an angle of 20 degrees. This is X, this is Y. This should all be coming back to you at this point. You want to find the X component of it? Say cosine 20 degrees is equal to X over 60. X ends up being equal to 60 times cosine 20. Which gives me 56.382. The Y component will be bound by the sine function. Sine 20 degrees is equal to Y over 60. We're going to say 60 sine 20 gives me 20.521. So that's good enough. We don't need to do F2 because it's the same values, right? It's the same angle, except one is opposite in direction, yes. Same angle, same magnitude, okay, same X and Y components, except one is opposite in direction. Here's my X's. Okay, let's say F net is equal to the sum of the forces. That's going to be FF plus F1 plus F2. We'll do the same thing for the Y component. F net is equal to FF plus F1 plus F2. Don't know what F net is. I'm not going to plug in M times A here for F net. Why not? What am I looking for? What am I trying to find here? Not A. I'm trying to find F. So why would I bother putting in M times A in there? F net is FF. FF is, what's the value of it there? For the X component, what's the value of FF? Yep. Good. Negative because it's to the left. Negative 85 newtons. F1. Who can get this one? It's the value of F1 that I plug in here. Yep. Good. 56.382 newtons. It's not 60 newtons. We only want the x component of it. And we just found the x component to be 56.382. What's F2? Right? Good. 56.382. We add those forces up, we end up getting 27.764 newtons. Is that my final answer? Is that my final answer? Go ahead. No, that's my x component of my final answer. Now let's do the y component. What's FF? Bless you. What's FF for the y component? This one's an easy one, I think. What's FF for the y component? Just wait. What's FF for the y component? Maddie, got that one? How much of that is y component? Devin? None. 0. Okay, it's all x. Right? We said the x component was -85. It was the whole thing. The y component, nothing. So let's cross that off. What's the y component of F1? Yep. 20.521. Good. Not 60. That was the whole thing. We want only the y component of it. It's 20.521 newtons. And what's the y component of F2? We know this one. Close. Negative 20.521. Now this one is nice because we add those up and it gives me 0. Right? So this one's nice and easy to combine, actually. How would we normally combine the x and the y? Draw a vector diagram and then do the Pythagorean theorem. When we're combining 27 and 0, though, what's the combined force? 27.764 newtons. Is that okay? These are not really new problems. They are and they aren't, right? These are really problems that we did last week with the net force is equal to the sum of the forces, combined with that vector analysis that we did in our last unit, where we found x and y components and analyzed it that way. Don't make it harder than it has to be. And don't, whatever you do, don't just memorize what you see up on the board. Hey, make sure that it makes sense to you why FF was -85 right here, but why FF was 0 over here. Why F1 was 20 right here, but -20 right here, and 56 here and 56 here. Okay, if that stuff makes sense to you, then you should be good to go on these questions. There shouldn't be any trouble at all. So don't just remember it, though. Understand it. Yep. Yeah, absolutely. The question, if you didn't hear it, was why is FF 0 again? We were told in that question 3.2 that force of friction is acting to the left, right? So if it's acting to the left, we have to include it. There's a force of friction there. But when we're breaking it up into an x and a y component, a left-right and an up-down type problem, then that entire force, 85 newtons, is in the left-right problem. How much of it is in the up-down problem? Now, part of this is because it's right and up. Part of this is because it's right and down. But this is just left. There's no up or down to it. So we make that 0 there. Does that make sense? Okay, copy that out if you haven't got it copied already, okay? Okay, let's take a look, please, at these two questions on page 134 and see what you can do with them. Just turning on the sound here. Just realized my sound was turned off. Okay. Just drawing out the diagram for question number 2. Our angle here for the second force is going to be 60 degrees here below the x-axis because this is 90, this is 180, this is 270. This gives me 300 degrees. That force is 70.0 newtons. We can say at 300 degrees, or you can say at 60 degrees, kind of below the horizontal axis. In the end, don't panic about that. Okay, if you can solve this when you have the diagram drawn in front of you, then you're good to go. Okay, don't worry about the 300 degrees if that messes you up at all, okay? Okay, I'll give you a few more minutes to work on these, and then we'll take a look at something here. All right, guys, we want to look at question number 1 here. Somebody was pointing out to me as we were walking around helping people that there is actually no force of friction here because they tell us in question number 1 that it's dragged along a horizontal frictionless surface. So this 85 newtons that we had in the other example, 3.3, is gone. All we have are these 2 forces, but these 2 forces are at different angles this time. Not 20 and 20, but rather we've got 20 and 40 degrees. All right, so what we need to do first is get the x and y components of both of those funny angles. We don't like funny angles. Let's get rid of them. Let's turn them into something that we can deal with a little bit easier. Okay, here's F1 at 60 newtons at 40 degrees. This is the x side. This is the y side. We're going to say cosine, right, Travis? Cosine 40 degrees for the x side, because it's the adjacent side, is equal to adjacent over hypotenuse. What's x equal there? 60 times cosine 40. I know a number of you have that. Yep. 45.96 newtons. We're going to do the same thing for the y component. Sine 40 degrees is equal to the y component over 60. And what's the y component equal there? 38.56. Here's a little hint, guys. And I don't know how many of you are thinking this deeply on it, but when you get an angle of 40 degrees, less than 45, you know your x component is going to be bigger than your y component, right? It has to be. If my angle is bigger than 45, then my x is going to be smaller than my y component. Well, I get a number here where my x is bigger, so I'm probably right. I've probably done it right. Let's do the other angle now. Let's say 20 degrees, 60 newtons. This is x, this is y. Let's say cosine 20 degrees is equal to x over 60. What does x equal there? 60 cos 20? 56.38 newtons. And let's do the same thing for the y component, except use sine. What's the y component equal there? The opposite side of that triangle. What is it? 20.5. Keep going. 20.50. Okay. Thank you. All right. Now let's break it up into our x's and y's for the net force thing. Let's say x, and let's say y. Let's say the net force is equal to the sum of the forces here. That's going to be F. We'll call it F1 plus F2. There's only 2 forces. F1 is going to be 45.96, Aiden? We really should have 3 or 4 decimal places, but we've only got a couple here because the person that gave me the numbers chinsed out a little bit and only gave me 2. But we really should have 3 or 4. The reality is if you go 2, you're probably going to be okay. But we're guaranteed pretty much to be okay if we go 3 or 4 or 5 decimal places. So we get 45.96 plus F2 is going to be 56.38. Right, the 2 x components. We add those up and what do we get? 102 point something? 102.34. All right, good. Thank you. Let's do the y component. Let's say F net is equal to the sum of the forces F1 plus F2. F1 for the y component is 38.56. Okay, here's the real test for you guys. What's the y component of the second one? I'm waiting. Who's going to tell me the y component of the second one? Bailey? It's what? Good. Negative what? Yes, good. Thank you. Negative 20.50. Why is it negative, Bailey? Good. They're both positive for the x component. Hold on 2 seconds, guys, to finish this. The x components are both positive because they're both to the right. But the y components, one's positive, one's neg because one's up, one's down. We add those together, what do we end up getting? 18.06. Now let's combine these together. Let's say we've got 102 to the right, and then we've got 18 up this way. 18.06 newtons up this way. How do you find that resultant vector right there? Yeah, you're going to do the square root of 102 squared plus 18 squared. And then how are you going to find that angle? The inverse tan function of opposite over adjacent. Is that good? Yeah, Travis? I don't know. They could have easily just said 104 there. That would have been fine. Yeah. All right. Make sure that if you haven't finished question number 2, make sure that you get it done for tomorrow, please. Okay? Have a good night, everyone.